Okay, so yeah, let's thank the organizers for bringing us all together, and in particular for bringing us together in a physical way and not just in a hybrid way, because somehow, at least my feeling is after having participated in some hybrid conferences, it's always a pity if you just see people on the screen, and it's really glad that we could be together. Okay, so I would like to talk a little bit about a project which is in fact even much, much older than this workshop here. And in some sense it's a little bit talking about some old stuff with some new wrinkles, and yeah, kind of promotional talk for something which I called relative oscillation theory. And should not forget the application and essential spectra of Sturm-Liouville operators. And that's a joint project together with Jussi, Carsten, who is also present, and Philipp Schmitz, who is not here right now. So let me just... Okay, so the topic is well known, I guess. We're going to talk about Sturm-Liouville operators. So I'm just going to use tau for the differential or differential expression. And here I'm really interested in the case where I have all three coefficients present. So sometimes it's just an exercise once you know how to handle the Schrödinger case to add the other coefficients, but sometimes it's not. So most of the time, as I said, if you know how to do general Sturm-Liouville operators, you can handle them. But there are some cases where this really doesn't work so well. Okay, I'm not going to write down any conditions on the coefficients. It's just the usual one, so local L1 for R and Q and for 1 over P, and I'm also going to assume that P is non-negative, and of course also R. And also remember that the associated or the appropriate Hilbert space here will be the one with the corresponding weight function right here. And I'm going to look at this as some general interval, which I'm just calling from A to B. Okay, there is also maybe one, maybe more associated self-adjoint operators. Which I'm just going to denote by H. Of course, you all know there is this limit point, limit circle classification, and depending on in which case you are, either you will need no boundary conditions or otherwise you might need some boundary conditions. Actually, the topic of this talk here is the essential spectrum of the associated operator, and it's of course also well known that the essential spectrum does not depend on the boundary conditions, so I'm not going to write down any boundary conditions because this is not going to be important for us. Okay, and maybe also recall there is a nice trick by splitting the intervals into two pieces, and then you know that the essential spectrum will be the union of the two pieces. So you can always assume that one endpoint, let's say the left endpoint, is regular. So that means we have a finite endpoint and the coefficients are integrable near this endpoint. So if you talk about solutions of the underlying differential equation, then you can start at this endpoint here by specifying initial conditions. Yeah, and the other endpoint then will be general, and yeah, so I'm going to make this assumption here without loss of generality. Okay, so let me recall, that's all well known, but still, how would you go about determining the essential spectrum of such an operator? Well, let's again, for simplicity, assume that P and R are equal to 1. So we just have a Schrödinger type operator. And then the standard approach of finding the essential spectrum would be, of course, to use some kind of perturbation theory, right? So in this case, we would use this theorem by Weil. We know if we have two operators and if we, let's call them H0 and H1, and if you know that the resolvent difference between H1 and H0 is trace class, so this is trace class. And this famous theorem by Weil will tell you that the essential spectra of these two operators are the same. So that basically means, if you want to apply this, find one operator where you can solve everything. Of course, you take Q is equal to 0, so the free operator, you know you can explicitly compute the eigenfunctions, you can explicitly determine the spectrum, and find out everything you want to know about this operator, and then you just need some conditions on the potential to ensure that this trace class condition here is valid. I see, I am writing trace class, of course, compact. In most cases, it will be trace class, but of course, compact would be enough. So this should be a compact operator right here. Okay, and it's well known that in some sense, in order to ensure this condition right here, you need something like the potential needs to vanish as x goes to infinity. So here I'm assuming that AB is just 0 infinity for simplicity, right here. So once you have this condition here, you get that your operator, your resolvent difference is compact, and you can apply this result by Weil right here. In fact, you can do the same thing if you just make the assumption that R is equal to 1. You can also include P, and the same is going to work. It's going to be a little bit more tricky to do the arguments, because then your perturbation also involves derivatives, and that's a little bit more complicated to handle than if you just have the potential term. But in principle, it boils down, P should go to 1 in a certain sense, and you still have the same result. Now, of course, the final question is, what if you also want to include this case here? Now, the problem in which you run is that the coefficient R shows up in your Hilbert space, right? So the problem is that the two operators live in different Hilbert space, and that's something which you not can easily overcome using this approach here. And in fact, if you look into the literature, you will find tons of conditions of finding the essential spectrum of Sturm-Liouville operators or of Schrödinger type operators. So where you have this case here, you will find a little bit less, but still you will find a couple of results which include the case where P is also allowed to be not equal to 1, but you will find virtually no results which also allow R to be different for both operators. Okay, and so this was our original motivation. How can we give some criteria in this case right here? And that's the promotional part of my talk right here, to say, look at oscillation theory, right? Because one way of understanding the spectra, and in particular of understanding the essential spectrum of Sturm-Liouville operators, is using oscillation theory. And the big advantage is that in some sense you relate the essential spectrum to oscillation of solutions, and you never need to touch any Hilbert space issues here in some sense. So this works in any case, no matter whether you have all three coefficients or whether you just have Schrödinger type operators. Okay, so that's kind of the idea of my talk. And I also decided I should probably be gentle on you. So I'm just going to recall some of the main ideas in hope to maybe refresh your memory if you have seen this, or if you have not seen this anywhere, then I hope still you should be able to at least grasp the main ideas here. Okay, let me start with the simplest case, and the simplest case would be classical oscillation theory, which of course goes back to Sturm and Liouville. So this is really old stuff here. Now, what is the idea? The idea in some sense here is count the number of zeros of solutions. So what do I mean by that? Okay, we have our differential equations. This is tau, and we pick some spectral parameter lambda. So we look at solutions of these eigenvalue equations. Of course, we don't have eigenvalues yet because we also would need to talk about boundary conditions, but we look at the solutions of this differential equation right here. We know there are two linearly independent solutions. We just take any one and we count the number of zeros of this solution here. Of course, for this to work, we should take a real valued solution, so also the spectral parameter must be real valued, and U, of course, should be non-trivial, so counting the zeros of the trivial solution is not going to give us any interesting results. So non-trivial and real valued. Okay, so the first thing one does in this case is one uses what is called the so-called Prüfer transform or Prüfer angles. So if you look at this second order differential equation, then usually it helps if you look at the system right here. So looking at the system means you kind of go into the phase plane and your two coordinates are u and the derivative of u. In the Sturm-Liouville case, it's a little bit better to add the p coefficient to the derivative. So you look at these coordinates right here, and now you're just using polar coordinates for these things here. So you write this as some rho times cosine of theta and rho times sine of theta. Now, of course, we all know when we use polar coordinates, then the corresponding angle, which is the Prüfer angle, will not be uniquely determined, but only it will be uniquely determined up to multiples of 2 pi. So what you need to do is you need to fix the value at one point. Let's say at the left-hand point, I have assumed this to be regular. So everything extends to this point here. So choose this. It doesn't really matter how you fix the multiple. Any multiple will be as good. And then make the assumption that it remains continuous, right? So if you follow the Prüfer angle, it will be continuous, but eventually it might jump. And then you just make sure that there are no jumps, and you just choose the multiple in such a way to get, so plus, I should write n. Okay, and so this gives you a unique, well-defined Prüfer angle. And moreover, you can read off the zeros of your solution, of course, by, it's of course just a convention, but let me still use the sign here because I want this connection of having a zero to be the same as the Prüfer angle at this point, to be a multiple, let's write it like this, of pi. Okay, so this connection is clear. Now the question is what happens at such a zero. For this, of course, you can easily take this differential equation here and write down a corresponding differential equation for the Prüfer angle. That's, of course, a nice exercise to do, but I'm not going to do this exercise for you. I'm just going to write down the corresponding result. So the result is this nice differential equation here. no minus. And there's the R here. Hard to read. So you get this differential equation. And if you look at this differential equation, in particular, if you evaluate it at a 0, what you see at a 0, this term here is going to vanish. You're going to stay with this term here. And of course, we have this assumption that P is always non-negative. So that means at a 0, the derivative is always positive. So that means at the 0, the function must always be increasing. So how does the situation look like? If I just make a little drawing, if I start at A here, then here we have the multiples of pi. Let's say this is pi, 2 pi, 3 pi, and so on. We fix our first value. Let's say we fix it somewhere here. Then the proof angle can do whatever it wants down here, so it doesn't have to be monotone or something like that. But at some point, there will be the first 0. So this is our first 0. Here we will cross the line P, and then we always can only cross it like this. So in particular, we will have a nice simple 0 right here. Might go like this, and then another crossing here, second 0, and so on, third 0 here, and so on and so on. So this is how the Prüfer angle looks like. And in particular, once you have the Prüfer angle, you can easily compute the number of zeros by just dividing the Prüfer angle by pi and then taking integer parts and looking at the difference. Okay? So in particular, you get that the number of zeros, let's give this a name. So the number of our solution n of u, you take the Prüfer angle at b. If b is infinite, you should think of this as a limit, but since it is essentially monotone, the limit will exist. And you have to use ceiling and floor functions. So here you have to use the floor function, and here you have to use the ceiling function. And you also have subtract -1, and then this gives you the number of zeros. The floor and ceilings function, of course, you need to make sure that you just count the zeros inside. And yeah, okay, think about it, and you can convince yourself that this here is the right expression for computing this number right here. Okay, now the next question is, of course, what has this to do with the spectrum? Now the connection with the spectrum, you see that, let's say theta of x, so I'm just looking at one point x, is increasing with respect to the spectral parameter lambda. Okay, so here everything, of course, depends, everything depends on this parameter right here, and one can easily compute the derivative with respect to lambda, just using the chain rule and working a little bit on this, and then you see it's going to be increasing. Okay, you can already see it from the differential equation here. This minus here will give you a plus. R is also positive. So that's a positive expression. There's a square, always positive. So it's the derivative is going to increase. So it's easy to see that it's going to increase. So that means if I increase lambda, for higher lambda, the Prüfer angle is going to look something like this. So what does this tell us? Well, it tells us, of course, that the zeros are going to move to the left. Okay? Moreover, since we have this property that at the 0, the derivative is always positive, that means all the zeros are always simple. So in particular, the zeros cannot collide. Okay? So the number of zeros is not going to decrease. It just can go up because zeros could enter our interval from the right right here, but once they're in the interval, they're going to move to the left and they can no longer disappear. In particular, if we look at a fixed boundary condition, that means we fix the Prüfer angle at this point here. So everything is going to start at the same point. So also zeros can kind of not disappear at the left of your boundary. So you see, number of zeros can only increase. And in particular, if you look, for example, at the Dirichlet operator, so if you have a Dirichlet boundary condition here, then you see 1 0 will enter from the right precisely when we have an eigenvalue. Because an eigenvalue means the solution vanishes at B if we look at Dirichlet eigenvalues. So you get this classical result right here that the number of zeros equals the number of eigenvalues, at least for a regular operator. Okay, but you can do even more. You can look at singular operators where it could, of course, happen that you have an infinite number of zeros, and then this tells you that you're above the infimum of the essential spectrum. Okay, how could you, for example, see that this is true? One way of proving this, and that's a nice observation, is the following. If you have your solution and these are your zeros, let's say x0, x1, x2, then a solution is going to look like this. And what you can do is, once you have this, I can say, okay, let's take, for example, this piece here, set it 0 to the left and to the right. This gives you a trial function. Okay, it's not going to be in the domain of your operator because you have a kink here, but of course it's going to be in the domain of the corresponding quadratic form. So it's a nice trial function. You can throw it into your Rayleigh quotient, and you see as many zeros as you have, as many trial functions you're going to get. And hence the spectral theorem tells you that there must be at least as many eigenvalues below this point. And in particular, if you have infinitely many zeros, you can compute infinitely many trial functions, and the spectral theorem tells you that your parameter lambda must be somewhere above the infimum of the essential spectrum. Okay, so that means whether when you determine if there's a solution which has an infinite number of zeros, then you know you must be above the infimum of the essential spectrum. So find this point where the behavior changes from non-oscillatory to oscillatory. This is precisely the infimum of the essential spectrum. Okay, so this only gives you the infimum of the essential spectrum, but it doesn't really allow you to compute the essential spectrum itself. And here comes the next thing, which is now the relative oscillation theory. And the idea now is take two solutions and look at the difference of zeros, right? So you take two solutions to, let's for the moment stay with the same operator, so one differential equations, two different values, let's say lambda and mu, and take the difference between the zeros of these two functions. Now the problem is, of course, if we want to find the essential spectrum, then both of them will be oscillatory. So I'm looking at infinity minus infinity, and that's probably not a good idea because that's not going to give you much information. But you could try to regularize this in the following sense. Take a finite interval, look at the difference, and then hope that everything converges as long as this interval grows, right? And this was the original idea, which I think goes back to Hartmann. So let me write this down. So idea is look at the number of zeros of one solution, u of lambda, minus the number of solutions of a second solution corresponding to the parameter p, that somehow this should correspond to the dimension of the range of the associated spectral projections of your operator corresponding to this interval right here, right? So, because this is precisely what you have in this situation here, the number of zeros gives you the number of eigenvalues. So if I take the difference of the number of zeros, I get the number of eigenvalues in between, and numbers of eigenvalues in between I could identify with the dimension of the range of the corresponding spectral projection for this interval right here. So one thinks that one could have this correspondence right here. Of course, don't take equality too serious, because if you take arbitrary solutions, things might change a little bit, but only up to plus minus small numbers. And we are only interested in the question whether this number is finite or infinite. So it doesn't depend what solution you take. And moreover, if you take the right solutions, you might even get equality right here, but that's not my topic for today. Okay, so as I said, the original idea was to look at this by Hartmann. There is a paper from 49, later extended by Weidmann in 71. So look at an interval AX and let x go to infinity, or let x go to b, to the other boundary point, and then you can identify this limit as the dimension of the spectral projector right here. Now, there was a related approach by Rofe-Betikov, who was looking at periodic differential operators. And he was interested in a similar question. He was not interested in finding the essential spectrum, because for periodic operators you can compute this and do the same perturbation arguments and so on. He wanted to know whether at a boundary point of the essential spectrum the eigenvalues accumulate or not. Again, that depends on the perturbation. And again, this could be answered by looking at this thing right here, looking at the difference. If this is infinite, then you know at the boundary there is an accumulation of eigenvalues. Thanks for pointing this out. So he looked at this case from 64, and actually he was using Prüferengel and something which he called relative Prüferengel, so a different approach here. So I'm going to come to this in a moment. So, yeah, and then much later, together with Fritz and Barry, we looked at this, and we used an approach, and you will see in some sense that's what Rofe-Betikov did, but just in disguise or in a different way, by not looking at zeros of solutions. Sorry, I'm not good today. Sorry, Fritz, for misspelling your name. Okay, so we were looking at zeros of Wronskians, and in the paper it was called renormalized oscillation theory. And I think Weidmann was the one who coined relative oscillation theory for this approach right here. And later on, together with my student Helge Krüger, let's hope I spelled Helge correctly. Okay, so we extended this approach here to looking at two different operators, which is what we want to do right now, because I would like to find out the essential spectrum of one operator, provided I know the essential spectrum of another operator. So some kind of perturbation theory. Okay, and it's still zeros of Wronskians, but it's not so simple in this situation if you have two operators, because you cannot just count the zeros. You need to weight the zeros in a certain way. But yeah, let me explain what the idea here is. So as I said, we're looking at the Wronskian. So I'm looking at two solutions of possibly two different operators. So I'm just using 0 and 1 as an index for tau 1 and tau 0. And the Wronskian in this case is just this usual expression right here. And if you plug in the Prüfer variables, then you can easily verify that it looks like this. So you basically get the difference of the two Prüfer angles, and this is the relative Prüfer angles, and it explains in some sense why it is the right object and why this here encodes precisely this behavior right here. Okay, and so then our definition for the relative number of zeros of U0 and U1, let's just look at it from A to X, so that eventually we can send X to infinity. So it will be just the difference divided by P with our floor and ceiling function, just as before. And the problem now is this is not going to give you the number of zeros of the Wronskian, because you no longer have this result that at a 0, this relative Prüfer angle is going to increase. That's clear because things are symmetric with exchanging the two functions. So if for one order it's increasing, it might be decreasing for the other. So you don't have monotonicity here, and you should think of this number here as some kind of weighted zeros, and you need to weight it depending on whether one operator is larger, locally larger than the other operator. Okay, I see I'm running out of time, so I'm a little bit behind schedule, but to bring this to a quick conclusion is, now this is the right object to look at, and as before, using similar ideas, you can define the concept of being relatively oscillatory by just looking at this number and trying to find out whether this is finite or not finite. Right? So if it's finite, I'm saying I'm relatively non-oscillatory. If it's infinite, I'm saying I'm relatively oscillatory. That's going to be an equivalence relation. It's not going to depend on the solutions you're looking at, and you will have the corresponding connection with the spectrum. So that means if it's infinite, there must be some difference between the essential spectrum of the two operators. And the idea of proving this is by again looking at this picture right here. So first of all, it suffices because you have an equivalence relation and some kind of triangle inequality. You just can, when you make the comparison, reduce this to the situation where you have the same operator with different parameters and different operators with same parameters. And the interesting part will be the one where you have one operator with different parameters. And the idea is, if you have the Wronskian and you look at the zeros, you can play a similar trick, because if the Wronskian vanishes, that tells you that the two solutions at this point locally are linearly dependent. So you can find a constant such that the two will match, and again this will give you a trial function. In fact, your trial function will even be in the domain of your operator. So the number of zeros gives you the number of trial functions. So if your Wronskian with different parameters, lambda and mu, has an infinite number of zeros, you see the difference between the spectral projections must be infinite dimensional. And then using this, you can, for example, show, if you look at this non-oscillation, if the oscillation behavior for both operators are the same, then the essential spectra are going to be the same. And that works for arbitrary operators with P, Q, and R coefficients. And if you're interested in more details, then of course you can look into our preprint where you will find all the details. Okay, so thanks for your attention and